Before steam, before electricity, medieval builders were already mass-producing timber with a river-driven saw that never got tired. Here's how they did it with water alone. Imagine standing beside a medieval river on a winter morning. Mist rolls off the surface, and above the noise of the current you hear something else, a steady, heavy rhythm, like a giant breathing. A wheel the size of a cottage turns slowly in the water, dripping and creaking. Every time one of its paddles bites into the flow, a long saw blade inside the mill jerks down through a log with a deep, wet hiss. The river itself is pulling timber apart, stroke after stroke, all day and all night, without a single laborer pushing the saw. Now picture the alternative. On a building site far from any mill, a gang of men straddle a pit with a heavy two-man saw. One stands above on the log, one below in the trench, both heaving up and down, teeth biting, sweat dripping. They work for hours to rip a single beam out of a trunk. Their speed is limited by their lungs, their muscles, and the length of the day. By the late Middle Ages, in some parts of Europe, that pit saw crew was already old-fashioned. Wherever there was a reliable stream and good forest, water-powered sawmills quietly multiplied the output of timber. A single mill could cut more planks in a day than a crew of men with hand saws, and it could do it in winter, in the rain, even at night, powered by nothing but gravity and moving water. In this video, the plan is to pull the walls off that riverside building and show you exactly how it worked. How medieval engineers took a river and turned it into a steady source of mechanical power. How they converted slow circular motion into the up and down bite of a saw blade. How those mills turned forest trees into ship planks, beams, and boards for a growing economy, centuries before anyone spoke of steam engines or industrial revolutions. Section 1. Water as the medieval power grid. In the ancient and medieval world, the first great leap beyond human and animal muscle was the watermill. By the 1st century BCE, Greek and Roman engineers already knew how to harness falling water to turn millstones. Vitruvius, a Roman engineer writing around the turn of the 1st century BCE, described vertical water wheels using gears to drive grinding stones. As the idea spread, streams across the Roman Empire sprouted mills, some undershot wheels where fast rivers pushed paddles at the bottom, some overshot wheels where water poured into buckets at the top and used gravity to pull the wheel down. What started as a way to grind grain quickly grew into a general-purpose power source. Archaeology and written sources show water wheels driving hammers in ironworks, fulling cloth, crushing ore, and, crucially, for this story, powering saws that cut stone and wood. One Roman-era site at Hierapolis, in what is now Turkey, has even given its name to a specific type of sawmill in the history books. By the High Middle Ages, especially in Western and Northern Europe, watermills had become a defining feature of the landscape. Domesday Book records several thousand mills in 11th century England alone, and later surveys suggest that mills were present in most towns and many villages. Grain mills were the most common, but wherever forest and river met, it was natural to apply the same moving water to the hard work of cutting timber. Section 2. From grain to saws. The idea of a water-powered sawmill. Mechanically, the leap from grinding grain to sawing wood is straightforward. Both jobs require turning raw flow into continuous movement. The difficult part is direction and motion pattern. Millstones want continuous rotation. Saws want steady reciprocating strokes. The first known machine to combine a crank and connecting rod, a system that turns circular motion into back-and-forth motion, was a water-powered stone sawmill at Hierapolis. On a relief from the 3rd century CE, A waterwheel feeds power through gears to two frame saws cutting stone blocks, each driven by a crank and rod. Similar setups appear archaeologically at Gerasa and Ephesus in the 6th century. Those early stone saws were Roman, not medieval, but they prove something important. Long before steam engines, craftspeople already knew how to take a turning water wheel and translate it into a saw's stroke. Evidence for specifically wood-sawing watermills appears patchier in the early Middle Ages, partly because wooden machinery doesn't preserve well. But by the later medieval and early modern period, written records and surviving examples make water-powered sawmills unmistakable. In forested regions like parts of Germany, Scandinavia, and the Alps, water-driven saws became critical to timber industries, turning local streams into engines for shipbuilding, construction, and trade. So what did a medieval water-powered sawmill actually look like, and how did it use water alone to chew through logs? Section 3. The layout: river, race, wheel, and house. From the outside, a medieval sawmill didn't advertise its complexity. It usually looked like a low, sturdy building perched beside a stream, with a large wheel half visible in a channel. The basic layout had a few key parts. The source: a river or stream with enough flow and drop. The mill race: a man-made channel that diverted some of that water towards the wheel. The wheel: a large timber construction with paddles or buckets. The gears and crank. Hidden inside, translating rotation into a sawing motion. The saw frame and log carriage, where timber met steel. First, the water had to be brought under control. Millers often built a small weir or dam to raise the upstream water level and create a head of pressure. From this mill pond, sluice gates fed a narrow race, essentially a long-lined ditch or wooden trough aimed precisely at the wheel. At the wheel itself, builders chose between different designs: undershot wheels, where the stream hit the paddles at the bottom and pushed them along. These worked in faster rivers with little height difference. Breastshot or overshot wheels, where water entered around the middle or top into built buckets. In these, the weight of falling water did more of the work, generally making them more efficient for sawmills that needed steady torque. The wheel was built largely from wood, with iron fasteners where necessary. It turned on a horizontal shaft that penetrated the mill wall. Inside the mill, that turning shaft was where the magic happened. Section 4. How moving water became a saw stroke. To cut timber, a saw blade needs to move up and down, or back and forth, in a controlled, regular way. A water wheel only spins in one direction. So medieval engineers borrowed and refined a clever mechanism: the crank and connecting rod. Here's the logic in plain terms. The water wheel's main axle turns continuously. Attached to that axle is a round disc, or a cam, with an off-center pin. A long bar, the connecting rod, links that pin to the bottom of the saw frame. As the axle turns, the offset pin traces a circle, and the connecting rod converts that circular path into a back-and-forth motion at the saw. If you have ever pedaled a bicycle, you already know the feel of this conversion. Your feet move in circles, but the bike moves straight. The mill reversed that idea. The river turned the crank, and the rod drove the saw. In some designs, the wheel's axle first turned a gear that drove a second shaft, allowing the miller to adjust speed or direction. In others, the crank was mounted directly on the wheel shaft. Either way, the result inside the saw frame was the same: a long vertical iron blade mounted in a wooden gate moved up and down in a regular, powerful stroke. The saw's teeth were shaped to cut on the downstroke. The upstroke lifted the blade back through the kerf with minimal friction, ready for the next cut. Gravity, plus the weight of the saw frame itself helped the downward bite. The force came from water. The steady rhythm came from the geometry of the crank mechanism. Section 5. The log carriage. Turning strokes into lumber. A moving saw is useless without a way to feed wood into it. Medieval sawmills solved this with another smart mechanism, a log carriage that advanced a tiny bit with each stroke. Logs were stripped of branches and bark, then rolled or levered into the mill. Inside, they were hoisted onto a heavy wooden frame, a carriage that could slide slowly towards the saw. Workers fixed each log in place with dogs and clamps to keep it from twisting. The carriage rode on rails, and its motion was tied to the same drive system that moved the saw. A common solution was a ratchet and pawel linked by rods and levers to the rotating shaft. Each turn of the axle nudged the carriage forward by a tiny amount, just enough for the saw to bite a sliver of new wood on the next downstroke. This automatic feed turned a series of discrete, water-driven strokes into continuous cutting. Once a log was set and the mill running, the saw would chew through it without need for constant manual pushing. Workers mainly monitored alignment, cleared sawdust, and reset clamps. The output was remarkable for the labor invested. A properly tuned water-powered sawmill could produce far more planks in a day than a team of pit-sawyers, and it could do this with only a small crew on site. That efficiency was why sawmills were often among the first industrial uses of water power wherever dense forests met usable streams. Section 6. Where and when? Medieval sawmills in Europe. So when and where did these mills appear in the medieval world? The technological foundations, waterwheels, gears, cranks, were in place by late Roman times, as the Hierapolis stone sawmill and similar finds show. After the collapse of Roman authority in the West, use of complex industrial watermills seems to have shrunk, with most surviving mills in the early Middle Ages focused on grain. As populations and economies recovered from about the 10th century onward, watermills exploded in number. Historians describe water power as a key technology of medieval Europe, with mills serving as the engines of everything from flour to iron. Grain mills were still the majority, but fulling mills for finishing cloth, forge hammers, and eventually sawmills spread in step with trade and construction booms. In forested, mountainous regions like parts of Norway, sawmills powered by water were operating from the late Middle Ages and into the early modern period. Institutions like the Norwegian Technical Museum note that water-powered frame saws became crucial for turning logs into export planks from the 16th century onward, representing an early wave of industrialization driven by water. Some historians argue that in parts of northern and central Europe, water-powered sawmills and similar machinery effectively created a pre-steam industrial revolution, allowing large-scale lumber production, mining, and metalworking long before coal and engines dominated. So while not every medieval village had a sawmill, many continued to rely on hand sawing. By the late medieval and early modern period, water-powered sawmills were key infrastructure wherever conditions allowed. Section 7. Economic and social impact. More timber. Different world. It's one thing to admire the mechanism. It's another to recognize what it changed. Cutting timber is a bottleneck. Ships, houses, bridges, barrels, wagons, tools, all depend on shaped wood. When every beam is ripped by hand, growth in construction is constrained by labor time and fatigue. Water-powered sawmills relaxed that constraint. In regions where they appeared, mills could process more logs into planks and beams in a season than traditional crews. That meant shipyards with steady supplies of standard thickness planks, towns able to rebuild faster after fires or expand building projects, export trade in sawn lumber, not just raw logs, which added value locally. Norwegian sawmills, for example, became major economic engines once frame saws and water power were combined. These mills increased timber yields and export volumes, concentrating wealth in the hands of forest and mill owners. In other regions, water-powered saws supported mining booms by cutting the timber needed for shafts and supports. There were social tensions, too. Like many forms of mechanization, sawmills threatened traditional craftsmen. Pit-sawyers risked losing work to the river. In some times and places, authorities limited or regulated sawmills to protect forest resources, manage monopolies, or maintain urban guild privileges. But in the long run, the logic was hard to resist. If a stream could replace 10 men with saws, and do so year after year with only occasional maintenance, anyone who controlled that stream had a serious advantage. Section 8. Limits and risks. When water turned against them. Water-powered sawmills were not magical. They had constraints and vulnerabilities that shaped where and how they could be used. First, they needed the right geography. Without a stream with enough drop, a sawmill would be weak or impossible. Droughts could slow or stop production. Floods could smash wheels and wash away dams and races. Second, they required significant upfront investment. Dams, channels, wheels, gears, saw frames, and buildings. These were not tools a single itinerant carpenter could afford. They were capital projects, often backed by lords, monasteries, town councils, or wealthy merchants. Third, they were mechanically temperamental. Wooden teeth in gears could break. Iron components could wear. The saw itself needed careful sharpening and tooth setting to cut efficiently, and mills had to be designed to safely handle heavy logs. Yet, despite these risks, thousands of watermills of all types dotted medieval Europe. Their ubiquity shows that the ratio of effort to output was more than worthwhile. Where logs and rivers coexisted, sawmills turned landscape into infrastructure. Section 9. Comparing hand sawing to water-powered sawmills. To really feel what these machines meant, compare the job they replaced. In traditional pit sawing, 2 workers straddled a saw pit. The log lay over the pit on supports. One man stood on top of the log, the top sawyer, pulling the saw up. The other, the pit man, stood below, pulling down and eating sawdust all day. Every stroke relied on human muscle. Keeping the cut straight required constant coordination and skill. A good crew could produce a useful volume of planks, but they tired. They needed food. They got sick. They argued over pay. The watermill, by contrast, supplied a nearly tireless pull. Once a mill was tuned, the saw stroke was perfectly regular. The log feed was consistent. The same human skill went into setting up the machine and maintaining it, but the river did the repetitive motion. This didn't eliminate hand sawing. Mills and pits coexisted, each serving niches. Remote sites without good streams still relied on human sawyers. Large operations near rivers centralized cutting at mills. But where sawmills existed, they shaped expectations of what was possible. A shipbuilder accustomed to mill-cut planks would design differently from one constrained by pit work. Section 10. What water alone really meant. The phrase, "cut timber with water alone," is poetic, but it hides a crucial truth. The river provided the raw energy. The rest was human design. Without carefully positioned weirs and sluice gates, water would either trickle uselessly or smash the wheel. Without a properly built wheel, the flow couldn't turn a shaft efficiently. Without gears and cranks arranged just so, the rotation wouldn't become a sawing stroke. Without a well-tuned carriage, the log wouldn't feed into the blade at the right pace. Seen from this angle, Medieval water-powered sawmills are less about free power and more about a kind of engineering literacy. Millwrights understood how much fall and flow produced usable torque, how changing wheel diameter altered speed and force, how strong gear teeth needed to be for different loads, how far to advance a log between saw strokes to avoid stalling or burning the blade. They couldn't write those relationships as equations, but they embodied them in wood and iron. Over generations, the best designs spread and improved. By the later Middle Ages, watermills were sophisticated pieces of technology, quietly as advanced, in their own way, as any early steam engine. Section 11. What you can learn from a medieval sawmill today. You might never build a water-powered sawmill in your backyard, but the logic they embodied is surprisingly relevant. First, they show what you can do when you start with the energy you have, not the energy you wish you had. Medieval builders didn't sit around waiting for coal. They looked at the nearest river and asked, "What can this do for us, exactly as it is?" For anyone interested in homesteading, off-grid life, or simply lowering energy dependence, that mindset is powerful. Second, they remind you that a low-tech solution can be deeply engineered. The components are simple: wooden wheels, shafts, gears. But the system is clever. It aligns materials, local geography, and mechanical principles into a machine that can run for decades with modest maintenance. Third, they suggest a different relationship to time. Building a sawmill was not a weekend project. It was a community investment. Once built, it served generations, grinding grain, cutting timber, sometimes powering several different machines with the same wheel. For a viewer who is curious, practical, and nostalgic, the lesson is not "go back to the Middle Ages." It's design small systems that can work with your landscape for a long time. Whether you're thinking about micro-hydro, community workshops, or just a more durable way of approaching projects, a medieval sawmill is a case study in long-term thinking. To close, come back to that morning on the riverbank. Inside the mill, the air smells of wet bark, sawdust, and iron. Each time the wheel turns, water slaps and spills, and the saw frame answers with its own heavy rhythm. Light from a small window catches the line of teeth as they rise and fall, slowly biting a thick log into straight planks. Outside, the river goes on doing what it always did, falling from hill to sea. Medieval builders didn't change that. They just learned how to borrow a little of that fall on the way down. They walled off a corner of the current, persuaded it to turn a wheel, and let that rhythm cut timber for ships, houses, and barns. Centuries before the word automation existed, a mill like this was exactly that, a machine where nature did the repetitive work. The sawyer's job shifted from pushing the blade to setting up the system and listening for the sound of trouble. The river was the engine. The millwright's craft was the interface. Today, when energy usually arrives as a bill instead of visible water or wind, it's easy to forget how concrete and local power can be. Medieval sawmills are a reminder that with enough ingenuity, you can turn something as simple as moving water into precise, useful work that shapes the forests around you into the bones of your world.